let's look at the first example. We need to find the radius of convergence for this series, and also we need to know where exactly does this series converge, which means we also need to find the interval of convergence. So this is exactly the same as asking you to find interval of convergence. Before we start this question, I want to go over what exactly do you need to do first, because that's a brief guideline for a lot of you, because I know some of you really need this. First of all, to find the radius of convergence, what you need to do is you need to apply, right here. So what you need to do is you need to apply either a ratio test. So ratio test, which is most likely what's going to happen, or root test, which is less likely to happen. Okay, to this series, then you'll get the limit. You'll get so let's say rho is a limit, right? This is ratio test or root test. Let me just recall it here. Or this. So that's my rho. So basically, you know that by a ratio test or root test, we know that the series converges if rho is less than 1, right? So you'll find rho after you apply the test, and then you'll say, well, the series converges if rho equals to 1. From this, you can figure it out my radius of convergence. So this is R. How do you know which one is which? So for example, you have 3 options. If your rho is already less than 1, so basically no matter what x is, right? Then that means my radius means it's always converge. So it means that it converges everywhere. So my radius is infinity. Then you don't really need to find there's no endpoint, so you don't need to check endpoints, you don't need to do anything, you can stop here. That's where your series converges, it converges everywhere, right? And the second case is my rho is less than 1, depends on what x is. So you might get something like x minus a is less than r, right? Then this is your radius. And option C is your rho is always greater than 1, no matter what x is. And that means you basically actually accept, I should make it clear, except at x equals to a, which is your center. Okay, that means you diverge everywhere except at center. So that means your radius equals to 0, because you only converge at x equals to a. That's radius of convergence, and this is like a brief review of what I said from before. And now, if you want to find interval of convergence, you would, for the second case, B, you also need to check endpoints. And what you need to do is you need to, so from here you would have x is in between r plus a and r minus a. So we need to plug in x equals to r plus minus a back into the original series. So back into this original series. And use alternating series test, or could be like test for divergence, so divergence test. Could be like comparison test or limit comparison test, or any other test. So it could be anything to check if they converge or diverge, and that's going to give you interval of convergence. So let's do this. Okay, after this brief guideline, which is like a summary of last video, let's try this. So here I'm going to apply a ratio test or root test, because I don't have to the power of n here. Root test is not really good here, so I'm going to use ratio test. And as I mentioned, most likely you're going to use ratio test a lot of time. So it's right here. So apply, so let an be -1 to the power of n times x to the power of n over ln to n. Okay, and then we can apply ratio test. What we're gonna have is limit n goes to infinity, absolute value of an plus 1, so change every n to n plus 1, -1 to the power of n plus 1, x to the power of n plus 1, and then ln 2 make sure you have bracket here, otherwise you might make a mistake. So ln 2 times n plus 1. Okay, here you need to be careful. It's a common mistake here. This whole thing is my an plus 1. Divide by an is multiplied by the reciprocal of an. So multiply by ln 2n over negative 1 to the power of n times x to the power of n. Okay, so this is what I have. And now we need to try to cancel out as many things as possible. The first thing that I noticed that I can cancel is this x to the power of n plus 1 and x to the power of n. So those two cancel out. You'll be left with x only here. And since we have absolute value, this negative 1 to the power of something does not matter anymore after absolute value. So this you can cross it out as well. And lastly, you have ln 2n and ln 2n plus 2, which there is nothing to cancel out at the moment. But we can bring it out. Okay, we can bring it out to the absolute value because as n goes to infinity, they're both positive. So you can take it out from the absolute value symbol. However, this x can be anything. Could be positive, could be negative, could be 0. So you cannot take it out of the absolute value symbol. So after all the cancellation and rewriting, what I'm going to have is this limit. So I'm going to have ln 2n over ln 2n plus 2 times absolute value of x. And since this x has no n inside, which means you can treat it as a constant and put it outside. You only need to evaluate this limit. So maybe I'll add one extra step here to take it outside because they are the same thing. So you can treat it as a constant because there is no n. So what we need to compute here is actually limit as n goes to infinity ln 2n over ln 2n plus 2. Alright. I'm pretty sure some of you already can see this is just 1, but for those of you who cannot see this is 1, I'm going to go over it step by step. If you can see it, you can skip this part and move on to the next part. But to compute this limit, if you plug in infinity, you'll see that this is in the form of infinity over infinity, which means we need to use L'Hopital's rule. So you can apply L'Hopital's rule. That's going to be limit n goes to infinity. Top is going to be 2n at the bottom, and chain rule, so that's just gonna be n plus, 1 over n, and bottom you would have 2 over 2n plus 2. Okay, and you can say, well, this one and this one cancel out, so you would have 1 over 2n times 2n plus 2 over 1, which is 2n plus 2 over 2n. So you can write that. Again, this is for those of you who cannot see it directly. You might need to do this. And thus, with the shortcut, a lot of you should know the shortcut by now. Top is polynomial, bottom is polynomial. They have the same degree as well. So you just need to look at the coefficient. That's going to be 2 over 2, which is 1. So that means my limit actually just equals to absolute value of x. So I'm going to move on to the next line because I'm running out of space. So this is actually absolute value of x. Okay, maybe I really shouldn't say it the last. Okay, it doesn't matter. And we are done with the first line here, apply ratio test or root test. And we know that by ratio test or root test, my series converge if and only if my row is less than 1. So this is my row, and I know that, well, it converges if and only if this is less than 1. So to write that down, by ratio test, actually, by ratio test, the series converges absolutely if absolute value of x, which is my limit, is less than 1. Okay, so this basically tells you, because this is basically in the form, right here, this is in the form of x minus a, absolute value of x minus a is less than 1, which tells you 1 is my radius, and my center is 0. Okay, so if you want, you can even draw the real number line and show yourself or the reader that this is what happens. So this is 1, and this is 0 because I'm centering at 0. So center at 0, radius is 1, so just going to be 1 and negative 1. So inside of this interval, we know that everything converge. And outside of those intervals, you know they diverge. But the problem is, we do not know for endpoints. So you still need to check endpoints. So continue here, we know that x is in between 1 and negative 1, and we need to check endpoints. So let's check endpoints. my endpoints, one of them is x equals to 1. So let's plug it back into this series. So that's gonna be, and at the top you have 1 to the power of 1, which is just 1, over long to n. Okay, so I just plugged in x equals to 1 into the original series. And let's try to simplify it. You'll get this. And this is just negative 1 to the power of n over long to n. Okay, clearly this is an alternating series, so we can use alternating series test. This is an alternating series. So let's let Bn be 1 over long to n, right? And clearly Bn is greater than 0, right? Because we're going from n equals to 1, which is long 2, which is greater than. So let's write the reason actually. Since long to n is an increasing function, is an increasing function, or just increasing. Maybe it's better because it's not really a function here. So since long to n is increasing and long 2 is already greater than 0, so the whole thing must be greater than 0. And also we need to show that Bn is decreasing, so you can check Bn plus 1. That's gonna be 1 over long 2n plus 1. Okay, which is clearly less than Bn itself. Why? Because, well, the denominator is bigger. Okay, so if you take the reciprocal of it, it's going to be smaller. So this should be clear, it's decreasing. And lastly, you should check the limit as n goes to infinity, Bn, which is 1 over long 2n, and as n goes to infinity, long 2n goes to infinity, so it becomes 1 over infinity. That's going to be 0. So by alternating series test, we know that it converges. That means when I write my interval, I need to include the point x equals to 1. Okay, so that's the first endpoint. Let's check the second endpoint, which is negative 1. So again, do the same thing. What we have is this new series. So at the top you would have negative 1 to the power of 1 instead of 1 to the power of 1, and then long to n here. And you should combine those two together. That's going to be negative 1 to the power of n. Sorry, this is summation, and then negative 1 to the power of n to the power of 2. So 2n, right? And negative 1 to the power of 2n, this is an even number. This is an even number. Negative 1 to the power of even number is just going to be 1. So eventually, we just have the series 1 over long 2n. Alright, so we need to check if this series, which is not really an alternating series anymore, so we need to check if this series converge or diverge. The first thing I would try is, well, test for divergence. If you quickly compute the limit, which we actually did from before, you know that it's 0, so we cannot use test for divergence. The next thing I can think of is probably comparison test. Okay, so let's try comparison test. What can I compare it with? Notice that I have a logarithmic function here. The thing about logarithmic function is that it's the inverse of exponential function, and we know that exponential function grows really, really fast, which means logarithmic function, they don't grow that fast. This property, if you don't know, let me just write it down for you. Remember, exponential function grows super fast, and then logarithmic function is the inverse of it, so they have the symmetry property, the symmetrical with respect to y equals to x. So this is y equals to e to the power of x, and this is long x. So to match with this, or symmetric with this, it's gonna grow quite slow instead of really fast. It's gonna be below. It's gonna be below this, right? In that case, from this you know that, well, long to n is definitely gonna be smaller than n. Okay, it grows slower than y equals to x, so it's gonna be smaller than n, which means if you take the reciprocal, 1 over long to n is going to be bigger than 1 over n. And thus is your Bn, correct? This Bn diverges by p-test. So let's write it down. This series 1 over n diverges by p-test, or p-series, since p is 1, right? and it's smaller than my AN. Remember, if your BN diverges, you need to pick the smaller one. It's smaller than my AN, so I can use comparison test. So by comparison test, some places call it direct comparison test. It's up to you whichever name you want to use. So by comparison test, we know that the series 1 over ln 2n diverges as well. After those two tests, or after you check the endpoints separately, our conclusion is that the first series, so when x equals to 1, my series converges, and when x equals to -1, my series diverges. That means when you write the interval of convergence, you should include 1 but not include -1. So we can make a conclusion. So therefore, the original series converges when x is in this interval. So I wanna include 1 but not include -1. So round bracket for -1 and square bracket for 1. And this is your interval of convergence. So use a different. Okay, so this is the final answer, and my radius is 1. Here, this is the radius. And that's the first example. We will do more example in the next few videos.